Electrical engineering exam questions. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, linguist, and bilingual teacher of mathematics and physics from Brazil. And in this video, I would like to invite you to a debate about the current, voltage, and power calculation in three-phase circuits. And for this purpose, I select several problems from the most important examinations for electrical engineers in Brazil. Let's begin with the first exercise. Exercise number 1 says, determine the power dissipated in the three-phase load of the following circuit. This is the question. Let's go to the solution. To solve this problem, it is necessary to recall that for any three-phase load, the complex power can be expressed as the complex power three-phase is equal to the apparent power three-phase in an angle. The apparent power is the magnitude of the complex power, and the complex power can be obtained from the multiplication as three-phase is equal to the square root of 3 times the line voltage times the complex conjugate of the line current, which is also equal to 3 times the phase voltage times the complex conjugate of the phase current, that is the complex power is equal to the active power plus the reactive power. The active power and the reactive power are real numbers, whilst the complex power is a complex number. In this way, P three-phase is equal to the apparent power three-phase times the cosine of the angle, and the reactive power three-phase is equal to the apparent power three-phase times the sine of the same angle. Since the load is purely resistive, the power factor is 1. The power factor is 1, which means that the cosine of the angle is 1 and the sine of the angle is 0. As the load is purely resistive, it does not exchange reactive power with the source. In this way, the reactive power is 0 and the active power is equal to the apparent power. The entire apparent power is being converted into active power. We can calculate the real power or active power multiplying 3 times the phase voltage times the phase current, but working with the magnitudes because the real power is a real number, not a complex number. 3 times 127 volts the phase voltage is 127 times the magnitude of the current. Observe that the magnitude of the complex conjugate of the phase current is equal to the magnitude of the phase current. And since this is equal to this, we simply divide the magnitude of the phase current is the phase voltage 127 volts divided by the resistance, which is 20 ohms. And this is equal to 6.35. 6.35 amps. And now, using this expression here, we can find the active power. P three-phase is equal to 3 times 127 volts times 6.35 amps. And we find, therefore, P three-phase equal to 2.42 kilowatts. Thus, we discovered that the real power dissipated in the three-phase load is 2.42 kilowatts. And this is all for the debate of exercise number 1. Let's go to the next. Exercise number 2. The exercise provided us this Y-connected load and asked us what is the value of the resistances in the delta configuration equivalent to the Y-connected load of the figure. This is the question. Let's go to the solution. Observe that for any given load configuration, balanced or unbalanced, the following is valid. ZA is equal to ZAB times ZCA divided by ZAB plus ZBC plus ZCA. ZB is equal to ZAB times ZBC divided by ZAB plus ZBC plus ZCA. And ZC is equal to ZBC times ZCA divided by ZAB plus ZBC plus ZCA. Note now that if the load is perfectly balanced, the impedance of the delta configuration is equal to 3 times the impedance of the Y configuration. In this case, Z delta is equal to 3 times 15 ohms, which is equal to 45 ohms. Therefore, the resistances in the delta configuration equivalent to this load in Y will be 45 ohms. And this is all for the debate of this exercise. Let's go to the next. Exercise number 3. A balanced three-phase load is connected in delta and supplied by a symmetrical three-phase source with a line voltage of 200 volts RMS. In each phase, the load consists of a 5 ohms resistor connected in parallel with an inductive reactance of 6 ohms. Determine the total active power consumed by the load. This is the question. Let's go to the solution. Observe that for the delta connected load, line voltages are equal to phase voltages. That is, for the delta, the phase voltage is equal to the line voltage, and in this case it is 200 volts. Also remember that only resistors consume active power, whilst the reactances exchange reactive power with the source. Because the resistor and the reactance are in parallel, both elements are subjected to the same phase voltage. That is, the resistor is directly connected across the source voltage. Therefore, the voltage across the resistor is exactly 200 volts independent of the reactance. Since the voltage across the resistor is known, the active power three-phase is equal to 3 times the phase voltage squared divided by the resistance, and for this exercise it is 3 times 200 volts squared divided by 5 ohms, and this is equal to P. 3-phase is equal to 24 kilowatts. The total average active power consumed by the load is 24 kilowatts. Note: when the load elements are connected in series, the phase voltage is divided between resistance and reactance. Thus, the current must be determined first, and the active power is then obtained from the resistive component of the impedance. And this is all for the debate of this exercise. Let's go to the next. Exercise number 4. A balanced three-phase load is supplied by a system with a line-to-line voltage of 220 volts. Each line carries a current of 51 amps and the power factor is unity. Determine the total active power absorbed by the load. This is the question. Let's go to the solution. For a balanced three-phase system, the total active power can be determined directly from line quantities independently of whether the load is connected in delta or Y. The appropriate expression is P is equal to the square root of 3 times VL times I. L times the cosine of the angle, in which VL is equal to 220 volts, IL is equal to 51 amps, and the cosine of the angle is the power factor equal to 1. If we calculate, we find that the P is equal to the square root of 3 times 220 volts times 51 amps times 1, and this is equal to 19.4 kilowatts. Therefore, the total active power absorbed by the load is 19.4 kilowatts. And this is all for the debate of this exercise. Let's go to the next. Exercise number 5. What is the total active power consumed by a balanced three-phase Y-connected load with per phase impedance equal to 10 plus J5 ohms, given that an emitter installed in series with one of the line conductors indicates an RMS current of 12 amps? This is the question. Let's go to the solution. The exercise didn't provide the circuit, but based on the information, we can come up with it. The circuit is on the board. Since the EMS current is given, the total active power can be determined using only the resistive part of the impedance. Note, power calculations in AC circuits are conventionally performed using RMS values. For sinusoidal quantities, the RMS value is equal to the peak value divided by the square root of 2. In this way, we can calculate the power. The active power three-phase is equal to 3 times the resistance times the current squared. And for this exercise, it is 3 times 10 ohms times 12 amps squared. And if we calculate, we find that P three-phase is equal to 4.32 kilowatts. Observe that if the same load had been connected in delta, it would consume 3 times as much power. This is for the Y. Had the load been connected in delta, P delta is equal to 3 times Py, which will be equal to 12.96 kilowatts. In the delta connection, each phase is subjected to the full line voltage rather than VL divided by the square root of 3 as in the Y connection. This increases the phase current by a factor of square root of 3. Since the active power is proportional to the square of the phase current, the total power becomes 3 times larger. And this is all for the debate of exercise number 5. Let's go to the next. Exercise number 6. A balanced three-phase delta connected load consists of 3 identical impedances of 5-phase 45 degrees ohms and is supplied by a line voltage of 220 volts. Determine the magnitude of the line current and the total reactive power absorbed by the load. This is the question. Let's go to the solution. The exercise stated that the load is balanced and delta connected. Also, the exercise provided the RMS value of the line voltage. Thus, we use the values provided by the exercise, the impedance of the delta connection, and the line voltage. The first step consists of calculating the magnitude of the line current. Remember that for the delta, the magnitude of the line currents is the square root of 3 times the magnitude of the phase currents, and the line voltages are equal to phase voltages. In this way, the phase current is the line voltage divided by the impedance of the delta connection. The magnitude of the phase current is 220 volts divided by 5 ohms, and this is equal to 44 amps. Thus, the magnitude of the line current is the square root of 3 times 44 amps, and this is equal to 76 amps. The total three-phase reactive power can be calculated using either line or phase quantities. the reactive power Q is equal to the square root of 3 times the line voltage times the line current times the sine of the angle, which is also equal to 3 times the phase voltage times the phase current times the sine of the angle. Let's use line quantities. Q is equal to the square root of 3 times 220 volts times 76 amps times the sine of 45 degrees, and this is equal to 20 kVAR. We therefore discover that the magnitude of the line current is 76 amps and the total reactive power is 20 kVAR. And this is all for the debate of exercise number 6. Let's go to the next. Exercise number 7. In the three-phase circuit shown, the source is symmetrical and the load is balanced and purely resistive. Both the source and the load are delta connected. A technician measured the magnitudes of the phase currents IA and IB and found 10 amps for each. With this information, determine the magnitude of the line current IC. This is the question. Let's go to the solution. The exercises said that both IA and IB are phase currents while IC is a line current. Applying KCL at the node, we obtain that IA is equal to IB plus IC. In this way, IC is equal to IA minus IB. Observe that this is a phasor operation. To work with the magnitude, we must use the following formula. The magnitude of IC is equal to the square root of IA squared plus IB squared plus minus 2 times IA times IB times the cosine of the angle. As IC results from the subtraction, that is the phasor difference IA minus IB, the minus sign is used. Here we are going to use the minus sign. For a balanced three-phase system, the angle is 120 degrees. And the magnitude of IA is equal to the magnitude of IB, which is equal to 10 amps. Substituting the values, the magnitude of IC is equal to the square root of 10 squared plus 10 squared minus 2 times 10 times 10 times the cosine of 120 degrees. Continuing, the magnitude of IC is equal to the square root of 100 plus 100 minus 200 times negative 0.5. which is equal to the square root of 300, which is 10 times the square root of 3 amps, or if you prefer, 17.32 amps. With these steps, we reach that the magnitude of the line current IC is 17.32 amps. And this is all for the debate of exercise number 7. Let's go to the next. Exercise number 8. What is the value of the line current I line in the circuit? This is the question. Let's go to the solution. The exercise provided this circuit here and this information and requested from us the value of the line current. One of the possible ways of solving this problem is to convert the delta connected load into a Y connected load. And I drew here on the board for you the converted circuit. As we previously discussed, the impedance of the Y connection is a third of the impedance of the delta connection. As the impedance of the delta connection is 15 ohms, the impedance of the Y connection will be a third of 15 ohms, which is equal to 5 ohms. Now let's consider the Y connected load of the circuit at the bottom of the board. As the load is perfectly balanced, it is possible to calculate the current in the following manner. The magnitude of I line is equal to the magnitude of the voltage divided by the impedance. But the impedance is not only the impedance of the load. We have to consider the impedance of the line as well. 5 ohms plus 5 ohms. And this is equal to 220 volts divided by 10 ohms. Thus, the magnitude of the line current is equal to 22 amps. Since the analysis concerns line currents only, and the delta Y transformation preserves the terminal behavior of the circuit, the line currents remain identical in both magnitude and phase angle for the original delta connected load and its Y equivalent. This is why the Y model can be used to determine the line currents of a delta connected load. Furthermore, as the circuit is purely resistive, the line currents are in phase with the phase voltages at the source. Note, although the line currents are the same in both representations, the phase currents differ. In the Y connection, phase currents are equal to line currents, whereas in the delta connection, phase currents differ in both magnitude and angle, being related to line currents by a 30-degree phase shift and a scaling factor of square root of 3. Thus, I line A is equal to 22 phase 0 degrees amps. I line B B is equal to 22 phase negative 120 degrees amps, and I line C is equal to 22 phase 120 degrees amps. And this is all for the debate of exercise number 8. Let's go to the next. Let's go to the last exercise. Let's go to exercise number 9. Consider a symmetrical three-phase source with phase sequence ACB and phase voltage magnitude of 168 volts. The phase voltages are defined as this. These are the phase voltages. The source supplies an unbalanced Y-connected load with the following phase impedances. These are the impedances of the load. Assume that the system is solidly grounded. Determine the line currents I1, I2, and I3, and the current flowing through the neutral conductor IN. This is the question. Let's go to the solution. Observe that as the load is unbalanced, the currents will differ both in magnitude and phase angle relative to each other. Thus, I1 is equal to V1N divided by Z1. I2 is equal to V2N divided by Z2, and likewise I3 is equal to V3N divided by Z3. In this way, I1 is equal to 168 phase 0 degrees volts divided by 42 phase 25 degrees ohms, and this is equal to 4 phase negative 25 degrees amps. I2 is equal to 168 phase 120 degrees volts divided by 24 phase 60 degrees ohms, and this is equal to 7 phase 60 degrees amps. And lastly, I3 is equal to 168 phase negative 120 degrees volts divided by 56 phase negative 75 degrees ohms, and this is equal to 3 phase negative 45 degrees amps. IN is equal to I1 plus I2 plus I3. To calculate IN, we convert I1, I2, and I3 to the rectangular form and sum the real part and the imaginary part. In this way, IN is equal to 9.25 plus J 2.25. Converting to the polar form, the magnitude of IN is equal to the square root of 9.25 squared plus 2.25 squared, and this is equal to 9.52 amps. The angle is the inverse tangent of 2.25 divided by 9.25. and this is equal to 13.7 degrees. In this way, IN is equal to 9.52 phase, 13.7 degrees amps. We have calculated I1, I2, I3, and IN, and this is all for the debate of this exercise. And it is all for this video, my friends. I hope you enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number. Goodbye!